All right, so there's this one weird thing that's killing furnaces and air conditioners. I'm Nate the House Whisperer, CEO of HVAC 2.0, and I wanted to take some time to make a video to follow up to the little 1-minute video that you may have just seen. So here's what happened. There's this one weird thing that's killing furnaces and air conditioners, and it is a new mandate that hit from the Department of Energy on July 3rd of 2019, and it changed from one type of blower motor to another that is generally more efficient, but not entirely. So if it's installed well, this isn't a problem at all. The curse is most aren't, and I'm going to show some numbers on that. So what's happening is only 2 years later, we're hearing about a surprising number of failures. I mean, so to lose a fan motor within 2 years is very unusual. So here's the story. And so the easiest way to understand this is to compare a heart to your duct system, because they work very similar. So the heart in your circulatory system to your furnace fan or heat pump fan in the duct system it's attached to. So the ideal thing is that blood pressure is just right. So you're between a 90/60 and a 120/80. If you are really high, between 160/100 and 180/120, you're at high risk for a heart attack. So your blood or your heart can't do what it is supposed to do, and it ends up failing. So you're asking too much of the pump. Same thing works for your duct system. So I made these two spectrums and made them line up. So if you get too low, it can be a problem. Like if you're really low, you probably have a big hole, you're bleeding out. You can be too low and there can be some risk there where you don't get good circulation to extremities. And the ideal is to be in the green range. Same thing with duct pressure. If you get too low, things don't flow very well at all. You want to be in the green range, if at all possible. You can get lower and it can still oftentimes work, but there's a limit to it. But on the low side, this is really not a common thing. Where on the high side, this is quite common, just with the heart. So looking at this again, between 0.08 and 0.3 inches of water column, that's the right amount of duct pressure you want to have. And I'm going to say duct pressure, but the technical term is external static pressure, but that sounds geeky and it doesn't necessarily make sense. So we just call it duct pressure instead. And external static pressure is the amount of pressure that comes both before and after your HVAC unit, be that a heat pump or a furnace. And the curse is, if you are on the high side, if you are over an inch of static, the fan may fail in less than 3 years. So this is what we're seeing already. I mean, that as I'm recording this, the regulation is just a hair over 2 years old, and we're already seeing pretty substantial failures. Even if it doesn't fail, if you're over a 0.7 and 0.7 inches of water column, which is what it's measured in, is generally considered where the risk factor begins. So even if you're above 0.7, the odds are your system's going to be noisy, and it's a very quick increase in energy use when you get higher static pressures, so it's probably going to be expensive to operate as well. And the curse is most systems are at risk of something not being right. And I'll show some data on that here in a minute. But first, let's talk about what the old kind of fan motor is and what the new kind is. What it stands for doesn't really matter, but it's called a PSC. These things are tough and they use a lot of energy. So I think of Jack Lambert from the Steelers. You know, that was a dude you didn't want to mess with. That's a PSC motor. The ECM motors are much more like a prima donna soccer player. You know, somebody touched this guy's ear and he, jokingly, of course, but he falls over like writhing in pain. So ECMs, it stands for electronically commutating motor. So it's an EC motor, not an ECM motor. These use much less energy if they're used well, but they're touchy. If you put them up against high static pressure, it's an issue. So here's old Jack Lambert, PSC. You can put it up against all kinds of static pressure. Doesn't care. They actually use less energy as the static pressure goes up. I picture like Scooby-Doo running away, with his legs spinning, but he's not actually going anywhere. That's how a PSC ends up working. An ECM, again, you get them over 0.7 inches of water column. It's not a good thing. Now, here's why this matters. So I pulled this from the news, air conditioning, heating, refrigeration news. And this is a table of what the Department of Energy's assumptions were. So this is the maximum external static pressure, which is duct pressure, that they were expecting. So units with an internal evaporator coil, that means a heat pump, basically. No more than half an inch of water column. Units designed to be paired with an evaporator coil. This is an air conditioner sitting on top of a furnace or behind a furnace, whichever way it works. Maximum of 0.65 inches of water column. And if it's made to go in a mobile home, maximum of 0.3. Let's look at some actual data in a minute here, though. So if we put it on the chart that I made, they're assuming between 0.3 and 0.65. That is their assumption. Now, this is an actual data set of actual tested static pressure in the field, and it is nationally representative for the United States. So these are real numbers. This is what we're actually seeing in the field. And you can see that it's a pretty spread out thing. But let's take a look at some specifics. So a half an inch of water column for most fans is what they are rated at. That's what you're supposed to stay under. Well over half of these systems tested above a half an inch of water column of duct pressure. So that is not good. So that is from here out. So that is orange and both reds. That is where over half of actual duct systems today are. Now, when we get to that 0.7 range that I was talking about, this is when the danger really starts showing up. And in fact, there is a meme about it. So high static, which is, again, another word for duct pressure. This is a meme from the HVAC industry. It's Pac-Man eating motors. This is super common. One of the fellows in the HVAC 2.0 group made mention that this regulation has been making him a ton of money on rental units because it's eating their motors quickly. So he's replacing like a dozen motors a week doing this. So high static, it's a real problem. This is not fear, uncertainty, and doubt. This is real. Now, what it works out to be is over 0.7 inches in this. This is a large data set. It's almost 800 systems, which is the largest data set I've ever seen of actual measured the duct pressure or static pressure. So it's something like 47% of systems are above that 0.7. That's not good. And when you get over that inch, like I said, this is where you have likely failure in 1 to 3 years. It's not a huge number of systems, but you're talking over 10%. So that's 1 out of 10. So there is a system on your street that is likely to die in 1 to 3 years, and it might be the one in your house. Now, if you get above 0.7 up to an inch, that is likely failure of the fan before the end of equipment life. And if you are to the point where you're out of warranty, this is about $1,000 replacement. And there's other problems it can cause as well. And again, I just want to highlight this is almost 50% of the systems in this test. And another key thing, this data set is made by contractors that are actually testing for this, which is maybe a few percent in the whole country. So the odds are extremely high that this is better than what the actual systems are in the US. So we're probably upwards of half of systems are at high risk of early failure. And so here's where that DOE assumption, where they said this is the maximum. Remember, 0.3 for mobile homes, 0.5 for heat pump systems, 0.65 for furnaces and air conditioners. They are assuming between 0.3 and 0.65. The reality is almost half of systems are above that range that they were thinking. This drives up energy use substantially. So you go from 200 watts of energy use as a system's running, which is like $20 a month worth of electricity, to 500 to 1,000 watts. Which is $50 to $100 a month in electricity if it's running all the time. This is a big deal. And then the systems fail early, and they're noisy. So all these things are not great. So let's look at what the main causes are. So we'll think back on blood pressure and a heart. So the main causes of high blood pressure are too much blood to flow because you're fat. So you've got lots more body that's your heart has to flow through. I mean, I'm totally guilty. Welcome to being an American. But this is hard. You're making your heart work a lot harder because it has more blood that it actually has to flow. And then constricted blood vessels, where there's garbage that's getting stuck in them. So those are the two main things: too much blood to flow and constricted blood vessels. When you translate that to ducts, what happens is you have too much air to flow, which is your HVAC system is oversized. It is trying to move too much air through too small of ductwork for the equipment. And this leads to the best solution. It's relatively simple. You want to downsize the equipment. So if right now you need 1,600 cubic feet per minute of airflow for your 4-ton system, if we can make it a 3, you need 1,200. And static pressure goes up. It's a square function. So it goes up very quickly as static goes up. So like one example, a system that I tested recently, I increased the flow 38% and it almost doubled the static pressure of that system. So I turned it down. So sometimes you can just turn down the airflow, but there's limits to what you can do, and particularly if you have single stage equipment. So downsizing equipment, which right sizes ducts, that is the best and really the simplest solution. And another piece of this, what it looks like, is you add what's called a BAD, which is a big air drop. I'll show you what that looks like in a minute, and downsize the system. We found this makes lots of things better. So let's start with what we jokingly call a SAD, which is a small air drop. So see this duct right here? This is coming down from the house. This is a basement system. You may not have basements where you are as you're watching this, but you have a big return duct like this, or actually a small one. And this is what they typically look like. They are 8 inches wide. So this thing's choked. Look how big it is coming out the other side and the supply side, and then the return side's really small. So this is a typical return drop, and that's the name, is a return drop. So the airflow here is going down, turning around, and coming up. But that air, when it hits here, air at these pressures looks just like water because it's not under a lot of pressure, so it's not being compressed. It's just flowing as a fluid, very much like water would. So when you ask it to hit this at high speed and make a turn, it's turbulent. It's not happy to make that corner. So here's what turbulent flow looks like. This is a river with a bunch of rocks in it, and this water is having to go around all of these rocks. It is not happy, and that's what's happening here. This is turbulent flow. And here's what this looks like. This isn't this exact system. I didn't test that exact system as I did the project, but very commonly you're going to see systems like this and see this is 1 inch of static pressure. This is quite common. Again, this means that the fan will seldom last even as long as 3 years. This is bad. Now, what the BAD looks like as opposed to the SAD. So BAD stands for big air drop. And all we really do here, it's really simple. Instead of having an 8-inch wide return drop, it's basically 24. This is not a ton of extra labor, and it's not a ton of extra materials either. So during install, this is not a big deal. Doing it separately is kind of a pain in the tuchus because you have to take everything apart. But now we have a large return drop, so the airflow is going down. The filter is big instead of a crummy little 1-inch filter, something like that. The filter's big, so all the air is hitting the entire face of that filter slowly, which means it works well. So this is going to make it so you have to dust less in your house because it's going to knock the garbage out. If you are concerned about getting sick, be that COVID or be that flus and colds and things like that, the respiratory particles will get stuck in this filter because they're going across it slowly, and it's a good filter. So that's a beautiful thing here. And then even though this is square, and this surprised me because I checked this system and I was like, wow, this is not the problem that I thought it would be static-wise. This is happy air. Because it's moving slowly and it's got a lot of space, it will make this turn and not be turbulent, which is a good thing. So happy air making that turn. And here's what that looks like. So when air is happy, it's called laminar. So this isn't a perfect example, but this is pretty decent. If you think about a wing, the reason wings work is it's turbulence. They make the air go further around on the top than it does underneath, which reduces the pressure here, and it sucks the airplane up. But in this case, you get turbulence on the top. Now, it's not super turbulence, but it's definitely more turbulent than it is below the wing. And so this is happy air. And because of the big air drop through here, we have happy air and laminar flow. So that's what you want to create. And this alone may be enough to fix your duct system and your high static pressure, but it might not. By the way, this is that exact system. So this is this system, 0.2 inches of static, which puts it right there in the green. We did not make any other changes on this aside from downsizing. We went from a big furnace, 120,000 BTU furnace, to a 3-ton heat pump. So we needed substantially less flow. Like I said, I didn't measure the static before, but the system was a bit on the noisy side, so I'd imagine it was probably in the 0.7 range when we started. But between the bad and downsizing, we got down to 0.2 inches of static, which actually made me nervous at the time because that's lower than you hear you're supposed to do. It ended up working, so I'm not afraid of it anymore. Now the bad, I should mention, this is part of Badass HVAC. I will link a video where I go into depth over this, and this is tackling what we call the 6 functions of HVAC, which is part of the HVAC 101 chapter from the Home Comfort book, my book. All right, now the other piece is you may add the bad, but also ideally you want to downsize the system. So you take it from heart attack range down to the likely post-install range. So very important. And so what you need to do is figure out, are you at risk? And we've talked about how well over half of houses are over half an inch of static, which is higher than they should be. And almost half of systems are above that 0.7 where you get the Pac-Man nom 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 eating ECM motors or EC motors. I will get a hard time for that. So the only way to figure that out is to get tested. So when you have an HVAC 2.0 contractor over to your house, ask them to run a duct pressure test. Now, if you find that you are at risk and you have a high number, you can do the bad. That might help. But the biggest thing is, can you downsize the system so it requires less airflow? This involves some risk, like you don't want to not be able to heat the house on a cold day or cool the house on a hot day. So there needs to be a little bit of testing, a little bit of math. Otherwise, everyone tends to oversize because you're afraid of that. Having done a great deal of downsizing myself, if you do the testing and you do a little bit of math up front, it's surprising how much you can knock it down. I mean, went from 120,000 BTUs to 36,000 BTUs. There's a very small handful of people in the country that would make that crazy move. And we're leading the charge of this through the HVAC 2.0 system. So what you want to do then, if you want to downsize, can you downsize? Get an HVAC 2.0 comfort consult. That's how you're going to find out if you can downsize, and if so, how much. And I should mention, in general, almost everyone can go down one size. So if you have a 100,000 BTU furnace, the odds are very high you can go to an 80, and they're pretty high you can go to a 60. But if you don't do some testing and lower the risk, your contractor is not going to be interested in doing that, because if it doesn't work, they're going to be on the hook for coming back, and they don't want to do that because that's a call when it's a really hot or a really cold day when they need to be out making money. There's times of the year where they make most of their money. And so they want to be doing paying work in those times, not fixing problems that they are on the hook for. So HVAC 2.0 Comfort Consult will help show you through all of that. But that is the overview. This is the weird thing that's killing furnaces and air conditioners. It's static pressure or duct pressure that is just too high for what systems are designed for. So they're using more energy. And if you are over that inch, you're very likely to lose that fan pretty quickly. And don't do that. You can have a test done and figure out where you are and then figure out what your next steps are. So I hope this was helpful in explaining duct pressure and the risks that are involved. Good luck as you replace your system. I'm Nate Adams, oftentimes known as Nate the House Whisperer. Have a wonderful day. Bye-bye.